This is the last deep learning classics and trends of this year. And we're welcoming Hattie Zhou back to give her maybe fourth presentation here. We can actually exactly count how many papers she has, and that's
all
talks she has given, which is great. All right, Hattie, the floor is yours.
Cool. Yeah, thanks for having me. This is my favorite reading group, so I'm excited to be back. So I will be talking about a recent paper called What Algorithms Can Transformers Learn? A Study in Lens Generalization. And this was done with folks from Apple MLR. And I would be happy to take any questions during the talk. Questions or comments or discussions, so we can make this more interactive. Okay, so we've all seen a lot of very surprising generalization capabilities for large language models. They can draw unicorns and ticks. They can solve math problems. They can even learn algorithms in context. And we want to understand kind of where this capability is coming from. But it's hard to study this in more natural settings because one, it's hard to define or formally define many of these tasks. And two, because we don't know what the training set consists of, it's also hard to study outer distribution generalization since we can't define the training and test split. And it's hard to do ablation studies for models at this scale. So our approach here is to simplify this problem as much as possible. We're going to focus on algorithmic tasks like addition and sorting. This is nice because we can fully control the train and test distribution. And we can ask a very interesting question of whether or not the model can actually learn the algorithm from just training on input and output data. So here we focus on the specific form of outer distribution setting that is focused on length. So we're going to train on shorter length examples and test on longer length examples. This is also interesting because for these type of problems, longer length correspond to harder tasks. And this is a nice proxy for whether or not the model has learned a generalizing algorithm. So typically, transformers really struggle with lens generalization. Here are some examples from a paper from Anil et al. They evaluated LLMs on parity and variable assignment. And we can see that on the x-axis, outside of the training length, which is the gray band, performance drops immediately. And this is pretty typical for lens generalization for these models. In some papers, like Ziri al, the Faith and Fate paper, suggests that transformer models only solve tasks through analogical pattern matching, which also suggests that maybe they fundamentally do not have the ability to solve problems systematically. However, on some tasks, transformers do exhibit generalization. For example, they can generalize to longer length for sorting. So the question is, can we understand when transformer models are likely to lens generalize? Or more generally, can we understand when transformers could learn algorithms or a generalizing solution when training on data? Okay, so I want to give you first an example of lens generalization. And here we're in the rest of the talk and all the experiments, we're considering transformer models, decoder early transformer models trained from scratch. So here is the counting task. For this task, we have A and B, and the output is the sequence of numbers from A and B. So here's an example, 5 and 8 is our prompt, and the output should be 5, 6, 7, 8, followed by an end of sequence token. Let's see if there are questions in chat. I'll try to answer as well. The models are pretty small, so I would say usually less than 1 million parameters, but there are also details in the paper, but they're not huge. So we're gonna train
So you
for
only train models for this task and nothing else. You don't train it with natural language at all.
yeah,
Okay.
models are trained from scratch only on a single task. So
when you're evaluating the size of the models, are they generally big enough to get perfect training accuracy as well as like good generalization within the domain? So maybe like train on A and B in these ranges and test on another A and B less than 60 that I never saw.
yeah, so for all of the tasks, we do train until convergence roughly. So they're all performing close to 100% on the training distribution. We also train in like an online setting, so no fixed training set. So we're always training and evaluating on the samples from the distribution, and we're training until the model can perform almost perfectly, if not perfectly, when possible. So at least there's one setting where this is not possible, but yeah, so here we're considering only out of distribution performance because you can assume training is 100%. So we're training on intervals sampled less than 60, meaning the length of the output would be less than 60. And then let's test them on length up to 100. And for this task, the models achieve 100% test accuracy without any fancy stuff, just training transformers from scratch. So how is this possible? Models never had to, I guess, output sequences of that length. And it's to understand how this might be possible, it's helpful to observe a couple things. One is a transformer model by design is running the same program on any length sequence. So it's the same model applied to any length in the context. So this can be seen as a program that we're applying to each segment. So the same model will apply to a shorter sequence as it would to a longer sequence. The second observation is for this task, there is an algorithm that solves it for any length. So in this particular case, the algorithm might be you look at the previous token you've outputted. If the previous token matches your ending token, which is B, so 8 in this case, then you should output end of sequence. Otherwise, you should increment the previous token by 1. So if the model learns this algorithm from training on shorter length inputs, then we should expect to generalize to longer inputs. So it turns out that this particular algorithm can be represented by a transformer model. And moreover, this is also simple to represent by the model. So question, how much training data did you use? So the training, I think this was trained for 10,000 iterations at a batch size of 128 or something like this. So we're just sampling that many examples from the training distribution.
Curious if, because you have a very specific form of the program here that would generate the correct answer for any length, could you probe the model to see whether or not this is essentially the program it learned? For example, run for 15 steps and then like change the previous token from 15 to 30 and see if it outputs 31 next, or other manipulations?
Yeah, that's a good question. So we did try to do some probing by doing counterfactual type evaluation. So if you present, say, a random sequence, will the model only pay attention to the last token and then increment that by one? So that's, for example, one of the steps we're testing for. Another one is, given a random sequence, on any token that matches the ending token, so 8 in this example, does the model always output end of sequence next? Yeah. And the answer is mostly yes, for models that generalize.
Cool.
So we don't know for sure mechanistically if this is exactly the operations being implemented, but there is some supporting evidence.
Oh, that brings a question. So when you train with an example, do you only have loss on the whole output, or you have loss everywhere?
Yeah, so we do have the loss on the whole output, and generally performance is maybe better if you mask out the output, but so like the prompt also have a loss, but this is pretty this is in line with how people normally train language models, so we just keep it that way. So actually, yeah, every token has a loss, but this is like, a lower bound for most tasks. We also pack the sequence or pack the context with multiple examples, which tends to help performance because it kind of tells the model to treat or to learn a program that applies to any location in the context. So in the context, let's say you have 512 tokens, you can pack, 10 different examples of this. And that generally biases the model to learn something that applies to every location. Yeah. Okay, what class of program? So let's dive into, I guess, the meat of this work. So we see that model. So how do we know that transformers can represent this algorithm? I'm going to answer that in a second, but here is the intuition that we're building on top of. So if an algorithm is simple to represent by a transformer model, we hypothesize that it is also easy to learn for transformers when just train out data. So if a solution is just simple for transformers, then we think it's more likely that they're going to learn something similar, and vice versa. So the question is, how do we define what is simple to represent for a transformer? And the answer is we're going to use something called the RASP programming language. Okay, what is RASP? So this is a programming language that was tailored for the transformer architecture and the unique information flow properties of transformer architectures. So in this language, every operation that you write can actually be directly compiled into a layer, or at most one layer of the transformer. And we can also realize this language as a very restricted version of Python. Okay, so some intuition for what this language tries to capture. You can only write parallelizable operations. And this is because a transformer model is inherently a parallel model of computation. So any operation you write should be a seek-to-seek function. So the input and output dimension of the operation should be the same. You can't have arbitrary loops or a control flow. And we're considering the causal version of this. So any operation can only depend on tokens that came before it. And this applies to intermediate calculations as well. And the main operations are the sequence map and the KQV, which we'll look at in more detail in a second, but this simulates an MLP and the attention layer. Okay, so for our purposes, we're trying to connect what is representable with what is easy to learn. And for that, we have had to make a couple adjustments to RASP, which we call RASP-L. And this is intended to capture what is easy for a natural kind of transformer to represent. So we add a couple restrictions, namely that all the variables should be bounded integers. And this is just to avoid arbitrary precision or numerical stability issues. Also, no arbitrary index arithmetic. So index arithmetic refers to arithmetic operations on positional indices. So for example, we don't know how to do things like get the middle index of the sequence. We can do this for the training length, but we don't know how to represent positional information in a way that would generalize to lengths that the model has never seen. So like, would the model know how to get the middle token of a sequence of length 10 if it's only seen length up to 5? So we don't allow this in RASP-L, and we also add some more aggregation options in the attention layer. It's just a minor detail. Okay, so, and we're gonna go through, I'm gonna try to teach you a little bit of RASP later, but with this, we can kind of reformulate our intuition into a pretty strongly stated toy model. For symbolic tasks, transformers tend to learn the shortest RASP-L program, which fits the training set.
Can I just ask like quickly how with this index stuff, like I'm just wondering how to understand it. So like say that we had like a transformer where like a generative transformer and had like its dimension, and each new one, it would take like the largest, I don't know, like the previous one, and it would add like +1 or something. So then like each of them would be like tagged with a number, and then like each of them could create like a key out of that number. And then if I want like to query like halfway through, I can take like my own number divided by 2 and then generate a query based on that, or some this kind of stuff. Or like, is the issue with that then you have like unbounded values or something, or like it's, I don't know, I'm just trying to build intuition for how like these things you can and cannot do with transformers.
Yeah, if I understand you correctly, you're saying like you can learn the number of your current index and then just divide that by 2 or something, and index or look up the corresponding value of that divided by 2. So the reason it's hard is we don't really know how to do this in a way that generalizes. So if you've only seen like from 1 to 10 positions during training, and you do this divide by 2 for 1 up to 10, can that operation generalize to length 20 for the model? The model doesn't know what length 20 is, I guess, in this sense.
Right.
So
but I was thought like, is the idea that if I could like program this manually in its transformer, then it could probably learn it too. Like I think you add some restrictions, right, on like your the maximum value, or like the L infinity norm or something, maybe that prevents me from doing this.
I think it's just how would you construct some type of positional embedding or positional information to allow this kind of operations, and yeah, to allow this specifically in a way that generalizes to numbers that the model has never seen in terms of indices. It's not, we don't know whether this is possible or not. I'm not saying it's impossible, it's just we don't really know how to do this. So it seems very non-trivial, and even more non-trivial that the model would learn something like this from training. But if you have ideas, I'd love to hear about how you might think
Yeah,
about like
there's probably
constructing.
some issue with my idea. I can ask you after. Thanks.
Yeah. I mean, this is a very interesting question though. We don't really know what's possible. But empirically, we'll see that this is very challenging. So with RASP is really helpful here because it gives us a measure of simplicity in terms of algorithms or programs. And this is essentially a minimum description length kind of intuition. Okay, so yeah, I don't know how much time I want to spend teaching people some RASP, but I guess we'll see. But if people find this boring or people want to, dive deeper, let me know. But here is an example of what RASP program would look like that solves the count task. That basically represents the algorithm we talked about at the beginning. And on the left, we just have the input and output of each of the steps, which corresponds to the line of code on the right side. And like I mentioned before, the main operations are the KQV and the sequence map. So I'm gonna dive in a little bit here. Let's just look at the first operation. And the goal of the first operation here is to identify the index of the start of sequence token. So to do that, we do this KQV thing, which generates a mask and then uses the mask to perform some aggregation on the value. So this is just very similar to attention. And yeah, so the select function generates a mask of 2 dimensions. And based on the predicate that indicates how you want to compare the key and query values. So for example, here, we're going to compare our X, our input, to a equal length sequence of the start sequence token S. So this comparison basically tells us when do we have S in the X input sequence. So we essentially generate this mask that does all the comparisons between these two sequences. And we can note this causal masking come into play here. So every S, I guess, can only compare to the positions that came before. And then we do this aggregation. So for each row, we want to take the index, the max index that has the value 1, which gives us 2 for everything that comes after S. So hopefully this gives you a kind of some idea of what it's like to program in RASP. It's pretty counterintuitive, but once you get the hang of it, it's nice to, it really helps to get intuition for what's natural for a transformer to do. Here's just another example. Now we want to get the index of the first number of the prompt. So to do that, we compare the indices to the start index that we got previously plus 1. So now we're just shifting by 1 and trying to find the, which values in the context is part of the prompt, essentially. So yeah, so we can do some simple operations on index information. Like we can compare it to shift by 1, shift by 2. We just can't do arbitrary operations on indices. But so things like plus 1, plus 2 is possible.
The fact that these variables are being computed, so you have count X is this like Python function. So start IDX is it's like a scalar value for a given position, or it's a whole time series of values, and you consider it being applied in a parallel sense. The fact that you compute start IDX on layer 1 and then start nums on layer 2, if you want a later layer to have access to all of that, should we assume that these are being like stacked together in like multiple multiple channels. Something
Yeah,
like that.
yeah. Yeah, I don't remember exactly how the compiler deals with this, but you can imagine them being like stacked in, or you can easily project out this information.
So like any later computation is allowed to use any previous
yes.
variable. Okay.
Yes. But only in a causal way.
Sure.
So like you can't do any computation that requires, aggregation over your entire sequence, like in the middle position, which sounds really abstract, but actually can be quite prohibitive when you actually want to represent programs.
Sure.
Yeah, that's a good question though. So yeah, we do have access to all the intermediate values. And wait, let's see if there's any questions. Okay, cool. Okay, so another set of operation that is pretty core is the sequence map, which takes in two sequences and then do an element-wise operation comparison between the two sequences. In this case, equals is the predicate. So here we're trying to find the position of the first output, which is, so the format is a little different here, but 1, 4 is the prompt, 1, 2, 3, 4 is the output. And for the transformer, you want it to be shifted to the left by 1. So we're trying to find where this should start. And essentially we take the indices and compare it to our start ID plus 2, which gives you this element-wise comparison between the two sequences. Variant of this is a token map, which only takes in one sequence and then do an element-wise operation on top of that. And this can basically be represented as MLP layers. Yeah, so okay, okay, so you can also compose many of these operations to represent more complicated things like the where function is equal to the NumPy version of where, but this is just using 3 seq maps, you can do this. So you can kind of build up from these simple operations. Okay, any questions before we move on from RASP?
There's a question in the chat asking, how should we think about the seq map's ability to perform any function? Should we think of function as an MLP or some sort of lookup map?
Yeah, we should think of, well, it could be both. A lookup map could be implemented as an MLP as well. We should basically, yeah, so there's, some limit, I think, to what an MLP could represent in practice. Here, we're not really putting on any restrictions, but there could be some gap between what you might write, what RASP might allow you to write in the seq map function that maybe is difficult to represent for MLP. But you should think of it as anything that could be implemented potentially by an MLP.
And so you could definitely represent something like skip trigrams in RASP, right?
Skip trigrams, what is that exactly?
It's from the Anthropic papers. So it's, where you have sequences like A ... B, C, where each attention head sort of selectively attends from like a token B to a previous token A, and then adjusts the probability of possible next tokens.
So this is like the induction head.
Yeah, exactly.
Okay.
Related to that.
Yeah, so that's very easy to represent in RASP. And we're actually going to see that come into use very soon. So yes, it's nice because induction has been kind of shown in models mechanistically, and it is also very simple in RASP. So they're consistent.
Yeah, no, that'd be cool to see.
Yeah. And if you look at the paper, we actually have the code for the induction head. So it'll be, for anyone interested, they can dig into that. Okay, so I want to come back to our toy model, and then building on top of that, state the main conjecture as it relates to length generalization. So here are the conditions we think are important to predict whether models will generalize on the task. First, the true algorithm should be possible to represent by a transformer. This is pretty obvious, but people don't really think about this when they're considering training a model on a task. Is the algorithm even representable by the transformer? For example, the parity algorithm is not representable by a transformer, but we're kind of evaluating the transformer's ability to generalize on a parity task when it's not really able to represent it in a generalizing way. Okay, and the second one is this representation should be simple, because then maybe it's more likely to be learned. And then the training data should be diverse enough such that there is no other shorter RASP-L program that fits the training data, but not the test data. So this is just the data diversity argument, but phrased in the form of what is the shortest RASP program that fits the training data. That one should be ideally corresponding to your desired algorithm. Okay, so how do we...
Can I ask a quick question before you
Yes.
continue? So I've heard it said that transformers have like the capability of universal function approximation. So they can theoretically model any function given sufficient capacity. Can you share like how you see that in the context of saying that only some algorithms can be represented? Like, are we assuming a certain small size or something?
Yeah, so we are assuming a fixed size of transformers, and we are also assuming this representing a program uniformly. So I think the universal approximation theorems all talk about like fixed input to output mappings, whereas like we're trying to ask if the model can represent an algorithm that would work on any length sequence, like an unbounded length sequence of variable size. And I think that is maybe not the setting that's considered for these theorems. So yeah, I would say two main differences. We're considering, fixed size models, and that would work on any unbounded length sequences. So for example, for parity, model could represent parity of any length if you just scale up the size of the model, but it may not be able to, like any fixed length, the model could learn to represent potentially. But can it represent an algorithm that would work for unbounded length is a separate question. Does that help clarify a little bit?
Thanks.
Yeah, actually, and can I jump in for a sec? And so that was kind of talking about unbounded lengths. So then that made me think about sort of, for instance, recently people are getting very excited about state space models and like Mamba. And so I guess the RASP would not be applicable to state space models. So we'd be talking about sort of an entirely different ballgame, right?
Yeah, so RASP would be specific to transformers.
Yeah.
Yeah. And RASP is very restricted also. So it doesn't capture everything that a transformer can do. So this is, a subset of what models can do. But it's pretty helpful for a lot of symbolic tasks, at least. Okay. Yeah. So let's see, how do we validate this hypothesis? We can come up with a set of tasks that we know have RASP-L solutions and a set of tasks that we don't know, at least, what if a solution exists. And we can evaluate models trained on these tasks and see if the generalization performance corresponds to whether they have RASP-L solutions or not. Okay, so going into the count example, here's what performance looks like. On the x-axis, we have the length that is over the maximum training length. So we have different experiments here that represent models trained for different length. So this yellow line here is trained for up to length 10. And then if you look at the first x-axis, this is representing 10 plus 10, so how the model performs at length 20. In this case, we're plotting test exact match at length 20 for this yellow line, and that's 80% accuracy. So, so here we're just aligning all of the length so that they're represented by, not by the actual length, but by how much longer is the model generalizing. And we can see that for these models that are trained on only a few different lengths, they have weaker generalization. And we also use this length as a proxy of training set diversity in a lot of these cases. But when you have up to, certain numbers of training length, like 50, 60, 70, 80, we're seeing pretty strong length generalization of up to 100, 150. So this is, it's not perfect length generalization, but it's much better than the very initial example I showed you, where generally performance degrades as soon as you go out of distribution. Here, they're generalizing to 2x or more the training length. Okay, here's another task on mode. I'm gonna try to go a little bit quickly over these results, but here we're trying to, given an input sequence, find the token that's the most frequent one. And this is nice because now the length is defined based on the input. So this is also kind of following a similar pattern. The shape's looking a little different, but there is definitely non-trivial length generalization happening here as well. And we have two versions of the copying task. The first one is when every token in the sequence is unique, and your task is just to repeat the sequence. The second version, there are only two possible tokens, and your task is to repeat the sequence, but there are only two possible tokens. So on the left side, we suspect that this is easy because this can be solved by using induction heads. You just have to look up where you are in the sequence by seeing what the previous token was. It gives you a unique position of where you are. You can't do that for the repeat token version. So it's likely you have to do some form of indexing to find where you are. And this is difficult to, and we don't know how to represent this. So it's not allowed in RASP-L. And here's what the performance of the two versions look like. We're visualizing this a little differently now. So we're plotting test exact match at length 50 on the y-axis. And on the x-axis, we're showing the maximum training length. So it's kind of showing us at what point of training length could the model start to generalize on length 50. So the max here is 45. And we can see that for the unique tokens version, model starts to do pretty well when trained on length 40. It can generalize to length 50. But for the repeat token, it's never able to generalize to length 50, no matter how much we give it in the training set. So this shows pretty stark difference between the two types of tasks, which, to us or to a language like Python, it's very similar, but for the model, it's very different. And then just to mention the parity thing again, because loops are not allowed, because constant depth transformers cannot represent arbitrary loops, if you have to do a certain number of operations or states that are unbounded, we don't know how to do that. And therefore, the parity task is unnatural for transformer architecture. It's natural for RNN because the RNN can keep track of state, but transformers do not really have this ability because it has to do every parallel computation to arrive at an answer. And there is only, a limited number of parallel computations you can represent in a constant depth transformer. So empirically, we also do not observe any length generalization. And for addition, we do not observe length generalization as well, but the RASP analysis gives us a very clear answer as to why is addition difficult. And the addition is difficult not because of the actual algorithm, but because it requires this index arithmetic operation so that you can refer to the correct digits at each step of your output.
Can I ask a question about the parity task?
Yeah.
The parity task seems like if you wrote a program and you just started at the last, the program has seen the entire input sequence and is trying to output the final answer, the parity, then you could not do that in a fully parallel way. So maybe it's not representable in RASP or RASP-L. On the other hand, I think you could write a RASP. Well, I'm curious what you think. Could you write a RASP or RASP-L program that would do the right thing by at every step computing like the parity of everything it's seen in the past, which could be done probably, like by just using whatever the last token had in that register plus this token's effect on the parity? Would that work or no?
So I don't think that works because you have to represent it in terms of like an input and output. So like what would the output of that operation look like? That would go into the input of the next function. It's kind of hard to think about, but
I see.
you can try it out. I think it doesn't really work, but you can imagine a parallel version of solving this task where you just sum up the sequence and then take the parity of the sum. So for that case, you don't have to keep track of a state at every step. But we also don't know how to do that because how do you represent the sum that are potentially larger than what you've seen during training and converting that into a parity? But we'll see. You can kind of improve this using a scratchpad because scratchpad gives you the ability to do some simple loops because it allows you to keep track of a state. So that's one way to get around this.
Cool, thanks.
Yeah, thanks for all the questions also.
One question I had was if this kind of, do you think this inspires you to make, architectural changes to the transformer? Like when you're kind of programming in RASP, you're like, oh, if I could only do this operation, I could implement all these algorithms, and then you like go back and being like, okay, well, how would we need to change the transformer so that operation could be doable? Is that like
yeah I think there are these adaptive kind of model architectures where the number of layers or number of operations can be adapted to the input sequence. something similar to like universal transformers, maybe. I think architectural innovations could definitely expand the capabilities, and RASP helps you maybe identify what the limitations of current transformers are.
Yeah,
So
and maybe
it would be
inspire.
yeah.
Like
Yeah.
has it already for you guys and like inspired like a new idea or like a new approach to transformers?
I think for some people, yes. Like this, you know, how do you build in this adaptive computation better? I think like indices is another problem that would be interesting to solve. Like, yeah. So I think so, but it's important to kind of consider what trade-offs you might have when you try to solve one problem. Maybe you introduce other issues. So I think that would be an interesting set of questions to look at, though.
Very cool.
Yeah. Okay. So we do see very strong correspondence with whether a task can be represented in RASPL and whether they show non-trivial length generalization. And what can we do with this? So this perspective kind of suggests two main levers we can use to improve length generalization. One is we can convert the task into a format that now has a short RASPL solution. The other one is just, can we increase data diversity such that we can remove other solutions that have short RASPL programs? And we don't have too much time left, so I'll go maybe a little bit quicker, but this is a very interesting deep dive on addition. How do we solve addition, basically through these insights? So we mentioned before that the index arithmetic is the difficult part of addition, this ability to refer to the correct tokens for each step. And we can kind of make this much easier by adding index hints, such as the A and B's here. So we can use these other tokens to indicate the position of the correct digits. So here, when you're outputting 3, you know you're looking at position A, and you can use induction head to kind of query where A was and then copy the next element, which is what an induction head does essentially. And with this, we can now write RASPL solutions for addition in this format. We can also further simplify the task by reversing the order. I think this is probably pretty intuitive because the addition algorithm we learn in school is in reverse order, not in forward order. But just to make it a little concrete, the reason is in forward order, when you output the first digit depends on whether there's a carry that comes from potentially all the previous or all the later digits in your answer. And so to output the 3 here, you would have had to compute actually all the previous ones potentially. So this is just more complex. And we can simplify this by reversing the order of the output of your answer. So both of these have RASPL solutions, but the forward one is much longer than the reverse one. And this is nice because many papers have observed that reverse addition is easier, but we provide a more rigorous justification for why. Because, you know, what is easier for us might not be easier for a transformer, but here we can show that indeed that is the case. Okay, so when we add these indices, index hints, for both forward on the left and reverse addition on the right, here we're still measuring at length 50. We see now that they generalize pretty well, at least starting from length 40. And this is on standard evaluations where we sample two numbers randomly. However, if we really push our evaluation by sampling really hard questions where there are this chain of carries that you have to calculate. So this happens pretty infrequently when you sample randomly, but this would be questions like, let's see, 37 plus 63. So to get the 1, you have to calculate all the previous digits. And when you evaluate on these questions, the forward addition is no longer generalizing, while the reverse is still able to generalize. So this kind of suggests that the forward model didn't really learn the proper way to handle carry, or at least as well as the reverse model. But we know that they both have RASP solutions. So we suspect that we can get better generalization on forward addition if we try harder. And one way to do that is we can increase the diversity of the training data by giving the model more of these hard carry examples during training. Because this is pretty rare when you just sample randomly. So the model just haven't seen a ton of these with the standard training distribution. Okay, and if we do that, the forward model is now able to do both the easy carry evaluation and the hard carry evaluation. So it's kind of matching what the reverse model would be able to do. And this is also a nice kind of confirmation of this interpretation that algorithms that are easy to represent are also easier to learn. So we can look at the training speed of forward and reverse addition. We can see that the reverse addition also trains faster, which is matches with our intuition here. Okay, I think since we're almost out of time, I'm maybe skip some of this last stuff in favor of any questions or discussions people have. But just quickly, we also can use this to understand when Scratchpad is helpful. And Scratchpad is helpful when you convert the problem into an easier RASP problem, and it can be hurtful if your Scratchpad actually does the reverse of making the problem harder in terms of RASP. So we see some examples there. Okay, well, yeah, so I'm just gonna pause here and take any last minute questions or comments.
Literally last minute.
Yeah.
Can you stay a bit longer, or this is here? You have a hard stop.
I can stay a bit longer, but people can feel free to leave.
Yeah.
Hattie, in your training, do you use a positional embedding?
Yes, so we use a learn positional embedding, and that is the best one also from some prior work in terms of lens generalization. We tried to use rotary embedding as well, and it's generally a little bit worse. But yeah, we just learned the positional embedding in these models.
But doesn't position embedding itself sometimes also prevent it from lens generalization? Like especially, I think when people try to forcefully use the trained position embedding, but test on a larger context lens, they need to interpolate the position embedding to make it work.
Okay, so we don't extend the context length, so it's a little bit simpler here, I think.
I see.
We only extend the individual example length. But the choice of positional embedding does affect performance, as do many other hyperparameter choices. So here we're just kind of, and this perspective doesn't cover, architectural design or training hyperparameters, things like this. And you can definitely train models that don't generalize on these tasks. But if you train them a little bit better, you can see a distinction.
Got it.
I have a question about the logistics of how the length is fed into the transformers. So if my understanding is correct, when the input length is short, there's some padding added to pass the input properly to the transformer. And then, but then the weights of the matrix that are connected to the padding, they're going to have no incentive during training to learn any useful things. So I'm just wondering how that generalizes then how those weights work for longer input lengths, because you're showing empirically that it does. Sorry if that's a silly question.
No, it's a good question. So we are padding the context with multiple examples.
Oh, okay.
So that's one answer, but there are still padding tokens. Actually, there are no padding tokens in these final results because we're also shifting randomly the padded
portion. Okay.
Just to simulate what's naturally done in language model training, where you just like take a random subset of a document in your context. However, I have tried only training on a single example. So you do add padding for all the later positions, at least for the count task. And what happens there is the model is a little bit worse, but it still generalizes. And basically, if you look at the positional embedding for the padded tokens, there's nothing going on there, whereas there is some information in the actual learned positions, but this doesn't catastrophically affect the performance of the model, which I think is because the model probably just doesn't use the positional information that much. In the count task, it's not really that useful either, if the model is actually implementing the RASP program. So in the case that it just doesn't really rely on that information, it's possible that the model is so generalized, even if the positional information is not meaningful.
Okay, interesting. Thank you.
Yeah.
I had a quick question. That's possible. So my understanding, thank you, by the way, this is really interesting. My understanding of this project was that most of the models were trained on a single task. What I was wondering is it possible, do you have any thoughts for extending this maybe to a multitask setting? And in addition to that, I guess if any comments for people that are interested in contributing to this work, direction.
Yeah, I think that understanding the interactions between tasks, I think is very interesting. And we had some preliminary results that were interesting. So it'd be probably a good direction to look more into. Basically, one question you can have is if multiple tasks share some component of the RASP-L program, and let's say they have different distributions on those components, could training the multiple tasks at the same time help one task learn from another task's like broader distribution? So for example, if you have a task that just does indexing and another task that uses indexing to do something else, and for your task that just does indexing, you have like a longer distribution during training, can the second task sort of leverage that, or can it learn from that to generalize better? Questions of that sort, I think, are very interesting. And yeah, just understanding how tasks can affect each other is a good direction, I think.
Okay, thank you.